Thank you all very much for coming today at our talk. I hope you all had a pleasant journey to Intel AMT world here today. Let me introduce myself. My name is Dmitry Evdokimov, and I'm a Chief Technical Officer at Embedded Company. My primary interest is security of embedded smart devices. I'm into code analysis, robust engineering, optimization with task, writing mostly in Python. I also maintain Python arsenal for robust engineering project. Alex?
Hello, everyone. My name is Alex. I'm a security researcher at Embedded, and also we should have here Maxim Malyutin, but he is absent. He is the founder, one of the vulnerabilities we found for this talk.
Yeah. So, on this slide you can see today's agenda. We will start with a basic of Intel ME and Intel AMT technologies. Then we will share our more interesting finding with you.
So, we'll start off today by taking a look at the Intel 64 system architecture. This is the typical desktop laptop system architecture. You can see that Intel CPU is definitely the main execution environment here. However, it is not the only one. There is also a chipset with integrated subsystems and controllers to support peripheral devices and other system critical functions. One of these subsystems is Intel Management Engine, or Intel ME. It is an isolated, stealthy, and most powerful execution environment here. The system firmware is stored on SPI flash memory. It is divided into a few regions. The main region is the flash descriptor, containing the sizes, offsets, and access permissions to other regions, so that the users of the flash could find its region and won't have access to other regions that for security purposes. So the next few regions, every region is belongs to the specific user of the flash. The gigabit Ethernet region stores the configuration for the network adapter. The ME region is designed for Intel ME firmware storage. It holds internal ME firmware binary. The RCPI embedded controller region has appeared since Skylake architecture. However, we have never seen it. So this firmware blob is included into UEFI BIOS, the last region of the flash. Every code. Any program code that is running on the system is executed in one of these CPU protection rings. We have the ring 3 with user applications having the least amount of privileges, and the most privileged mode for the CPU is ring -2, system management mode. Such code is executed from hidden space in DRAM called SMRAM. It is not seen at any other level before it. So, however, we were able to gain access to ring -3, the most powerful execution environment here. It is an Intel ME. It has even more access capabilities and memory isolation techniques. So now we are going to go more in depth with its architecture. It is based on MCU with ROM memory and SRAM memory. It consists of a MAC-level controller, host embedded controller interface or management engine interface, UMI memory in DRAM, and firmware, ME firmware, which is stored alongside with the BIOS on the SPI flash. This subsystem is generally thought as the most privileged execution and hidden execution environment, and there are a few reasons for that. For one, the UMI memory is hidden from the CPU. It is not seen for it in any protection ring. Additionally, it has full access to DRAM and out-of-band access to the network interface. And the funny thing that management engine still works even if your device, if your computer is turned off but plugged into an outlet. This subsystem is integrated in any Intel-based Intel chipset, Intel-based system since 2010. Its name varies depending on the platform type. Year by year, the interest of researching this subsystem, Intel Management Engine, has increased. The main problems with reverse engineering this technology are as follows. Intel MIA firmware code modules use syslib functions implemented in the boot code, which is stored in ME ROM memory. It is inaccessible for the CPU, of course, and sometimes it is difficult to understand the function behavior in ME firmware, which is calling these syslib functions. But fortunately, ROM images can be found in the debug versions of ME firmware. Another problem is that the code partially compressed with a Huffman algorithm with unknown compression dictionary. However, the dictionaries have been already reconstructed. There is also an undocumented HEC, or Host Embedded Control Interface communication protocol. It is an undocumented interface, but the protocol could be reverse engineered. The ME UMI memory is still inaccessible for us, and an open source society has created a heading to disable this hidden and stealth environment, but there are no stable method to do this on our systems. So if you're interested in reverse engineering the Intel ME firmware, you will need to disassemble and diffuse script presented here. Keep in mind that this presentation will be available on our website, so don't worry about copying everything down right now. Also, there are few useful links if you are interested to understanding this broad theme. So, to understand the following segment of this presentation, we would like to provide the basics of Intel ME firmware. So, its code is divided into modules, and depending on the system, the code module list varies. So, however, there are basic modules such as bring up, the loader, and the kernel, some drivers and services, which is present in every firmware. There are also the application code modules that implement different Intel technologies. Basically, there are three firmware types. The ignition firmware, which is actually only available for MBA version 6 and with the minimal firmware size and contents. Then we have 1.5 megabyte firmware, which has incomplete module contents. And lastly, the 5 megabyte firmware, which is the full firmware contents. So Intel AMT active management technology is implemented as a code module inside Intel ME firmware. The technology itself is meant to remote control and administration of computer systems. It allows remote powering on and off the system, resetting the system, accessing the BIOS setup through serial over LAN feature. Also, it allows getting the environment, the information about the system hardware installed through the web interface. And it allows booting the system from the custom boot image or file through IDER feature. And it allows acquiring the full control of the monitor, keyboard, and mouse of the system through the KVM feature or remote desktop, it is called. Any of these features required the Pro brand to have for the system. Usually it means that the chipset with vPro brand should be present on the system. There are several ways to access the Intel MT features, remote or locally. The remote access is available through the wired or wireless network interfaces, starting from certain versions. Messages received on the wired LAN and addressed to certain ports are intercepted by management engine prior to reaching the operating system NAT stack. Messages received on the wireless interface go to the host wireless driver, and which detects the destination port and sends the message to Intel MT. Various local applications are available to access Intel MT features the same way network applications do. For example, via WS management over SOAP or HTTP. When a local application sends message addressed to the local internet, to the local Intel MT hostname, the LMS, local manageability service, listens to the traffic directed to the hostname and intercepts the messages, routes them to Intel Management Engine interface or host embedded control interface. Here are well-known network ports that are used by the remote administrator to access Intel MT system.
Thank you, Alex. I will take the floor at this point. Moving on to the next section of our presentation. Let's have a look at the possibility of unauthorized remote access to Intel MT system. The first thing to do is to look from user's point of view at how the things are arranged. When users access the Intel MT web server via the 16992 network port, they are referred to the login page and the challenge with a standard authentication require request. So let's use Mitigation proxy. Now, with the help of a proxy server, let's analyze what is actually happening in more details. RFC as for RFC 2617, that is authentication. The first request gets a response with unauthorized code 401. So then we are given a correct username and password. The server accepts one as a legitimate user. When given an incorrect username or password, the server doesn't accept one. This kind of behavior is not surprising at all. On this slide, you can see network traffic of successful attempt. So nothing extraordinary has happened during the authentication process, but the detailed look at the sniffed packets give us a clue what to look for in the ME firmware. It is authorization header field names. We can use these strings for searching through the firmware and pinpoint the very code that is responsible for the digest authentication. For purpose of reverse engineering, we will be use the IDA Pro disassembler and special loader scripts. This plugin was written in Python, and it has a support ME format in IDA disassembler. It should be work for all firmware versions prior to 10. It's code available on our GitHub page. So, and after the loader completes parsing and otherwise processing the firmware, we'll have a nice and clean look onto the present code and data. On this slide, you can see IDA windows after analysis. A quick search for the strings like username, real name, nonce, synonce, response provide us with the exact strings within a next stack model. As we can see, they are all cross-referred from the one particular function. This function is responsible for authentication header fields processing and the overall digest authentication. After a careful examination of function code, we have found an interesting bug. The exit place of that bug is in the final comparison of the provided and computed response. The two values were tested against each other to see if they match. but the actual number of bytes to be tested was taken from the user-provided response, not from a computed one. This if one provides an empty response string, string compare function returns 0, as a number of bytes to be compared is 0. 0, it means successful authorization. It's bug. It's easy bug. So let's repeat our previous experiment, but with a local proxy. In order to exploit the newly found vulnerability, one can use a Mitigation proxy tool with a simple script that blanks the response field in the authorization header of outgoing request. It is a very simple script which has a small size, about 10 lines of Python code. So the web browser is configured to access the network through the local proxy at 8080 network port. The password we have just typed in is obviously incorrect because the Intel AMT doesn't allow the password shorter than 8 characters, but we will give it a try. The first request gets the same response like in previous experiment, it's okay. But then, voila, please take a note on the value of the response field is empty, and we server response, which is 200, it's okay, it's successful authorization. So the attacker is now authenticated as a legitimate system admin and has full access to variety of the Intel AMT controls. He can do absolutely everything without knowledge of password. We checked with vulnerability on other Intel AMT versions from old to new ones. To check them, we simply use proxy without any reverse engineering. After that, we reported this vulnerability to Intel, and then the vendor offered to us to participate their private bug bounty program on HackerOne, and we were given a $10,000 award. As you must have understood, it is authentication bypass vulnerability, which was later to be known as CV 2017-5689. This vulnerability was originally discovered in February this year. For successful attack, only need system based on Intel CPU in chipset, where only need is active Intel AMT services. For successful attack, we not depend on software. We can successful attack Windows system, Linux system. Only Mac system not affected because this code is cut from where. The general idea is attacker possibilities and Intel AMT capabilities as the same thing. Especially they can use the Intel AMT functionality to achieve their malicious purposes. So what about impact? According to the showdown, to May 2nd, there were 6,378 available IP with Intel AMT. It should be taken into consideration that showdown data covers only the internet, while a good deal of Intel AMT are used in corporate network. This corporate AMT can easily be used by attacker who has connected to a network. The most affected industries, telecom providers and universities. It turned out that this vulnerability had affected ACS. For instance, a Siemens industrial computer based on the Intel chipset were sensitive to it. In other words, not only enterprise and public organization, but also critical infrastructure may be affected by the vulnerability exploitation. So now demo time. Saving. Yeah, configure a web browser for access to the network through proxy. Start Malyutin proxy tool. Login the system. Then start Malyutin proxy tool with our script that just blanks response field. Try again. Admin and obvious incorrect password. It successful authorization on the system. That's all. So, about mitigations. Excuse me. After a blog post went public, to enable a network security company was able to rediscover our vulnerability despite not having any access to the technical details of the vulnerability. It is really impressive work. And then after we released technical details, the security community developed many useful tools and scripts, especially for this vulnerability. One of the most interesting tools being honeypots. The existence of these honeypots make it impossible to know how many real Intel AMT systems accessible from internet now. Mitigation. Well, Intel created patch for this vulnerability and then provided it to all affected OEM vendors. Following this, all affected OEM vendors created new firmware, which is now available for users to download. Because this vulnerability exists at the firmware level, you personally need to update it. It won't happen automatically. So how many people really install it with patch? For example, this hall. How many people? Yeah, not many. Of course, after patch releasing, we checked a downgrade attack. But Intel ME firmware could be easily be downgraded if the SVN was increased, SVN number was increased. In that case, the flash write access is needed. So the system with unlocked SPI flash regions, in most cases, the access permissions properly configured. So sending host message flash protection override to Intel ME using the hard drive SPI flash program should do the trick.
Thank you, Dmitry. Of course, it's all good and well, but this is possible if Intel AMT is officially supported on the system, if this technology has been already activated. We wonder if it's possible for attackers to spread out the coverage of this vulnerability and the Intel AMT itself for their own goals. So, as you know, Intel AMT is a part of Intel vPro brand. First of all, we wanted to understand how exactly the vPro system differs from the non-vPro one. Well, the non-vPro system is cheap. We checked that non-vPro system and vPro system may have absolutely similar Intel ME firmware images, so that Intel AMT implementation is often present on the non-vPro system. Thus, there is Intel AMT code in all 5 MB firmware versions. It turns out that the main difference is the presence of the Intel MEBX module in the UEFI BIOS and some options in BIOS tab. It's this module that uses a host embedded control interface or management engine interface to configure Intel AMT. However, maybe there are hardware restrictions, or how can we interact with it and make it work? The host embedded control interface seems to be a useful communication channel with Intel ME. It could be used in the debugging purposes to gain the status of Intel ME and the system itself, or to retrieve some data. Unfortunately, it's a pity the command system is not public. So this interface is a bunch of registers in PCI configuration space and memory mapped input-output. It represents a circular buffer which should be used to send or receive messages in a special format. The messages should contain a command. After the message is sent to Intel ME, the acknowledged message with the command status should be responded. There is an Intel driver designed for these purposes in the system. You can see it in the device manager. The driver maintains the communication with Intel ME. The message protocol itself is based on the DCMI-HI protocol. To send a message, you need to know the ID of the specific client you want to communicate with. Also, there are some known clients with a certain set of capabilities. In our case, to configure AMT, we should use the AMT-HI client. The format of these messages varies depending on the HC client is used. So for the AMT-HI client, the following format should be used. As you can see, the messages have the group ID field, meaning the common group identifier. Each group has a specific set of commands, so we should specify the group ID, common code, the ID of the client, and send these messages one by one to configure Intel AMT. After sending this message, after sending each message, don't forget to receive the acknowledge. And a very important moment, Intel MABIX module is absent inside the UEFI BIOS on non-vPro system. So there is no user interface for enabling and disabling AMT. So user can disable AMT after activation, after we have activated it. Also, for deactivation, you need to send another command and reboot the system. And the funny thing is that the knowledge of the password is not needed. So it occurs that there aren't any hardware restrictions, well, at least for some systems we have checked. Maybe this is OEM's fault. As a POC, proof of concept, we have created a tool to activate the Intel AMT technology on the systems, both vPro or non-vPro. The activated consists of the following program components. It should be used, should be run with the administrator privileges. Then you can remotely use any feature of Intel AMT. So we have prepared the demonstration movie for you. So now we on the system 1 trying to connect to the another non-vPro system. The attempt was unsuccessful. We go to the system 2, which is non-vPro, deleting, uninstalling the management engine interface driver to show that we don't need it. Then we use Intel AMT activator with enable argument. After some time, it enables Intel AMT and assigns this IP address to this system. So we are trying to reestablish connection to it. To the Intel AMT network port, and as you can see, this attempt was successful. As you can see, we are connected to Gigabyte motherboard with H97 chipset, which is not vPro. Okay, thank you. So, current version of AMT activator has experimentally gained some limitations for usage. Only 6 to 9 Intel desktop chipset series are supported now. Successful AMT activation on 100 and 200 series chipset not yet achieved. Intel AMT configures to standard manageability mode. This means that you won't be able to use the KVM feature if your CPU is non-vPro, the CPU, not the chipset. The AMT activation is possible on the systems with Intel ME 5 MB firmware versions. As I have already said, the 1.5 MB firmware doesn't have such functionality implemented. This tool is currently Windows only, but it can be ported onto Linux. It uses our kernel drivers for its operation, but it can be implemented to work with the already installed Intel Management Engine driver as well. So maybe you guys are thinking about the possibility of Intel AMT technology being used in the malware. So for malicious code using Intel AMT, it's worth nothing there. First, Oleg Bakov researchers have already come up with this idea in their research. Second, quite recently, Platinum, a malicious program, has been detected in the wild. The Platinum uses the Intel AMT serial overland feature to secretly communicate with the command center. In both cases, the malware does not use a vulnerability in Intel AMT. So, as Microsoft stated, this channel works independently of the operating system, rendering any communication over it invisible to firewall and network monitoring applications running on the host device. How can we mitigate this problem? Well, the community suggests several methods. However, none of these techniques are perfect. In some cases, the attacker has a countermeasure for that. If you're a company that uses Intel AMT frequently or even infrequently in your corporate network, you simply can't block this port in the network firewall because it is needed. And then you can always use an ME cleaner script to remove this functionality. However, this is dangerous and can break your system. We didn't stop here and went on. We had the question to be answered. What can a potential attacker do if the system has 1.5 MB firmware without Intel AMT implementation? This firmware image could be swapped to 5 MB firmware to add the absent Intel AMT implementation to this system. This part of our research is in progress now, however, we have the following results. The obvious way to swap the 1.5 firmware image to 5 MB firmware image on the system is to use an SPI flash programmer, hardware programmer. This will allow to bypass the flash regions locks, but some systems have SPI flash regions unlocked, so this opens a way to do the same from the software. The administrator privileges are required to do that. You can use a kernel driver or exploit local privilege escalation bias vulnerabilities in system management code.
Thank you, Alex. So, what can attacker do by using Intel AMT? This table demonstrates what is possible with chipset series. As you can see, there's still some question marks. This because there are many systems with many different configurations. For us, this is still a work in progress, but it would be great if you could help us with this vendor. This slide demonstrates how attacker would maneuver through your system. For the attacker, we'll check to see if your system has AMT enabled, and if you do and it's not patched, then the attacker can just go ahead with the exploit to use your Intel AMT. However, if it is patched, the attacker can attempt to activate AMT or increase the size of the firmware and then activate AMT to use your Intel AMT functionality. The thing is, because the Intel ME is ring -3, it occurs at the lowest level. People themselves have to patch this firmware, which is likely going to be rare. This means that this vulnerability will exist a very long time. So, takeaways. We have established today how easy it is for an attacker to exploit our vulnerability in Intel AMT web server. We also showed you how an attacker can activate and deactivate Intel AMT on vPro in non-vPro system through undocumented features. And finally, we demonstrate how it's possible to swap firmware image from 1.5 megabytes to 5 megabytes for the goal of aiding Intel AMT system. We hope that our research has shed light and brought awareness to the security issues in the ring -3 phases. So, thank you for your attention.
Thank you.
Thank you very much. Any questions from the floor? No? All right, well, great. Thank you very much again.